Okay, then welcome everybody to the next edition of the webinar series of ISPRS Working Group 3.3, Active Microwave Remote Sensing. And I'm happy that today I can welcome Dr. Tamer ElGharbawi. Tamer holds a PhD in Civil and Earth Resources Engineering from the Kyoto University, Japan, achieved in 2015. And in December 2018, he was appointed as an assistant professor of civil engineering at the Suez Canal University, Egypt, where he has been promoted to an associate professor of civil engineering at the same university in January 2024. Tamer is a specialist in SAR interferometry and geospatial analysis with over 10 years of academic and consulting experience, and has contributed to multiple large-scale surveying and geoinformatics projects across Egypt, Thailand, and the whole Mediterranean region. Also, he has served as a co-investigator in the 2025 ISPRS Scientific Initiative on forecasting of coastal displacement, and has been actively involved in the development of AI-based atmospheric correction tools and advanced GIS workflows for civil infrastructure and environmental engineering. And I think this is also already indicating the direction of his talk today, because he will talk about atmospheric correction for InSAR. So I think without any further ado, Tamer, the floor is yours, and we're looking forward.
Thank you so much, Michael, for this nice introduction. First, I would like to welcome everyone in this webinar. Today, I will focus my talk about a very critical process in the InSAR processing, whatever the platform or the SAR sensors, which is the atmospheric correction for InSAR. We have been developing many methods to correct for this kind of errors in atmospheric, in InSAR or in interferometry. And recently, there has been the development that reaches to other areas like neural network and global modeling. So in this talk, I will go through all of, the atmospheric corrections in the process of InSAR. So my outline is actually to see the atmospheric delay challenge, why it is important to correct this atmospheric delay. Then I will go for the atmospheric delay correction. It can be broadly divided into classes. So it's divided into merely 4 classes, and we're going to go through one by one. And then I'm going to discuss which methodology or which class can be used for the InSAR interferometric correction. And finally, I will conclude with the challenges and future direction in this topic. So first of all, what is the InSAR? Just a quick introduction. The SAR images, like we can see in this figure, we have the SAR sensor, or the antenna is actually moving in the azimuth direction and have a side looking, and it covers a lot of large region according to the swath. But this is only a SAR observation. It suffers from many delays and many effects. It's only can be effective, or the error can be visible, when we use the InSAR images in interferometric. That is using 2 images and calculate the difference between them. So the main idea, or the main problem, is in the difference in the range. So if we just write the general equation of InSAR, it contains about the topographic effect, the deformation, the tropospheric, ionospheric baseline, and noise. And one of the most crucial errors are the tropospheric and ionospheric delay. These 2 delays combined, we call it atmospheric. So it's atmospheric divided into tropospheric and ionospheric. These mainly mask the deformation signal that we are interested in. So in this figure, we can see that the SAR satellite, or the signal of the SAR satellite, is actually propagating through the atmosphere, and then it goes through the ionospheric layer and then the tropospheric layer. The ionospheric layer is mainly above the 50 kilometer of elevation. It is the main issue that it is dispersive. It is like ionized. It has free electrons in this layer. So it mainly affects the SAR delay based on the frequency. For the tropospheric delay, it is mainly from the zero elevation or from the ground level up to nearly 50 kilometers. It is frequently independent. So it is the effect is nearly the same for any sensor. And it can be divided into two main components, which is the dry component caused by the air pressure, and the wet component caused by the water vapor. Some researchers have divided these effects into stratified and turbulent. The stratified is mainly the depending on elevation, and the turbulent is actually that is not depending on elevation. So this kind of atmospheric delay is mainly multiplied by 2, mainly because we have like two-way path for the InSAR signal, traveling from the satellite to the pixel and then traveling back. So it is this effect of the atmospheric delay is multiplied. So why we are even caring about this? So first of all, it can mask some kind of deformation. We have here an interferogram. This interferogram was generated using ALUS Pulsar 2 for the Nagano region in Japan. It was affected by an earthquake. We can see here that the temporal frame from October to November, it is merely 2 months, and the atmospheric delay is merely masking this kind of deformation. After correcting, we can see the fringes of this earthquake, and we can study it. However, we can see in some of the topography, there is still residuals from the tropospheric delay, which is actually correlated to elevation. So we can do some improvement, or we can do some corrections for the atmospheric delay, but it's not nearly perfect yet. So one of the problems we have for the earthquakes, for the atmospheric delay, that it actually masks the deformation we are trying to observe. Another thing that it can mimic the real signal signatures. Here we have the Suez Canal in Egypt. This is a Sentinel-1 C-band interferogram. It's from October to November, merely 1 month of temporal delay. We can see here that this kind of atmospheric delay is actually showing some kind of fringes. It can be mistaken for some kind of depression or elevation in the ground, but it's mainly totally is atmospheric delay or tropospheric delay, because this is like a C-band. So we can see here that when we are using this kind of interferogram without correction of the atmospheric delay, we can mistakenly identify some deformation that is not existent. So this is for the C-band. For the TerraSAR X, the X-band, this is the interferogram for Bangkok, Thailand. We can see that there is a lot of fringes here, and this is actually highlighted by the short wavelengths of the X-band, because when we have a delay, it is wrapped based on the wavelengths of the signal. So we can see, even though this interferogram have very short temporal time frames, only 2 months, and there was no deformation happening in Bangkok at that time, we can see that a lot of fringes exist in the atmosphere in the interferometric SAR using TerraSAR X. So the phase actually can reach ranges of 15 to 20 centimeters. So in order to remove that, it is essential to get some kind of accuracy. So we can see here in the left is actually an interferogram using ALUS 1 in the Chiba region of Japan. There is no deformation in this time frame. We can see that a lot of fringes is actually masking what's actually happening. Actually, there is nothing happening in this time frame. There was no deformation, no earthquake, no nothing. So as you can see, after correction, we can get a clear interferogram or a clear unwrapped phase. And comparing the standard deviation of these two images, we can see that before correction, we have a standard deviation of nearly 40 millimeter. And after correction, it becomes a 4 millimeter level. So this shows the extent of the atmospheric delay effect. For the ionospheric delay, it is actually, as we mentioned before, it's about the ionospheric layer, which is actually dispersive, mainly because the sun ionizes the upper layer of the atmosphere. We can see here in this animation that the red region or red regions actually have a higher atmospheric delay, or higher ionospheric delay that is dispersing the signal and causes a lot of fringes. And this is actually very damaging to the InSAR. As we can see here, that it can cause some kind of streaks in the L band. It mainly affects on the L band. I'm going to talk about this wavelength dependability. and it can cause some kind of fringes. It can cause a stripping pattern, and even in other sensor that because the look direction of the pixel or the image itself, the sensor can the signal can pass through an ionospheric delay in the beginning of the swath, and another pattern in the end of the swath, which can make the pixel are blurry. So in order to see what is the importance of this kind of ionospheric delay, we have like the lower latitude region around the equator. It has mainly a lot of error due to the ionospheric, and has to be corrected. We can see here that the equation of the ionospheric delay is mainly dependent on both things. In the slant total electronic content, which is actually the number of free electrons in the layer of the ionosphere, and it's inversely proportion to the square of the frequency. We can see here in this graph that the long wavelength of SAR is actually highly affected by the ionospheric delay rather than the shorter wavelengths. These kind of fringes are actually can be seen in any L band or B band InSAR. And to just get a grasp of the effect, here we calculated the delay at 1 total electron content unit. It's nearly 50 centimeter for the L band and 2.7 centimeter for the C band, and merely 8 millimeter for the X band. And the thing is, the ionospheric has a long wavelength effect. So for the C band and the X band, it can be removed along with the baseline correction. So for the L band, we have many researchers. The main thing is actually the split spectrum method, which was adopted from the GNSS processing or the GPS processing, because the GPS have two frequencies, L1 and L2, and by exploring that the ionospheric delay is actually depending on the frequency, we can do what we call like ionospheric free signal. Mainly, instead of just focusing the image for the entire band, we just separate it in two bands, lower and upper. And using this kind of equation that have some kind of that show the relation between the delay of the ionosphere between the upper band and the lower band, we can estimate this kind of frequency, this kind of delay, the ionospheric delay, and correct the interferometric images. So we have correctly identified use the split spectrum for correcting the ionosphere. So is this more to it? Yes, there is. We have like new missions now. One of them is actually the ISPRS, which actually have two bands, the L band and S band, and it is dedicated to cover the whole globe for the canopy height and environmental impacts. So using this kind of technology and the umbrella, as we can see, that actually makes the signal even wider to cover a lot of region, and using two frequencies, the L band and S band, this actually requires like testing new methodology that can correct this kind of effect, especially the ionospheric delay for this kind of mission, in order to be feasible and can be used adequately for many processes. Another thing that the ALOS 4 has now been launched, and actually the L band as well as its predecessor L1 and ALOS 1 and ALOS 2, and it actually can benefit a lot from this kind of ionospheric correction. So for the now I'm moving from the ionospheric delay to the other layer, the tropospheric delay. The ionospheric delay was actually frequency dependent. So we have like an equation that can determine it. Unfortunately, for the tropospheric delay, it's actually frequency independent. It's very turbulent. It can have high variability according to the weather, according to the climate, according to the topography. And this is actually make it very difficult for us to correct. We need to study this kind of tropospheric delay effectively in order to get a reliable deformation from the InSAR signals. So it's mainly have like a spatially correlated component, and it's temporally uncorrelated component. This is like the main effect or the main characteristics of the atmospheric delay. So this is like Alexandria in Egypt. As we can see here, this is like Sentinel-1 C band. It is this interferogram is nearly less than 1 month in temporal space and a temporal time frame, and you can see that we have a lot of fringes that actually can be mistakenly identified as subsidence or something like that. This region in this like 1 month, they didn't have this kind of effect. So in order to correct that, we need to correct this kind of region, mainly because the coastal region in the Mediterranean Sea is now very vulnerable to the rise of the sea level and many other things that makes this kind of region is very vulnerable. And we have like the climate change that has been affected for like the Derna in Libya that have like a massive floods. And in Alexandria city itself, there is many buildings are subsiding currently in a very low rate due to this kind of effect of the atmospheric and the climate delay. So in order to get this kind of deformation, we need a very sensitive process, a very accurate process for correcting these kind of errors. So the main problem for this kind of effect is actually we have the SAR images is actually observed in a slant mode. So in order to correctly calculate this kind of delay, we have to integrate this refractive index over the inclined path of the signal, which can be very intensively a process for the InSAR processing. This can be done for a single interferogram. Now we have like the big data is coming in. So we have like more than 2,000, 3,000 interferograms we can study for a single region. This process of integrating or ray tracing the atmospheric delay through the atmosphere can be very demanding. So this kind of effect is actually one of the essential parts in correcting the atmospheric delay. So in order just to get a grasp of this kind of thing, we can see that for that stratified tropospheric delay, which actually the delay that depends on the elevation or correlated to elevation, we have like a delay of from 5 to 15 centimeters, depending on the location, and the spatial scale is nearly 10, about like 10 or more than tens of kilometers. So for the turbulent, this is the most crucial part, the turbulent tropospheric delay, which actually a localized noise. We can remove the stratified tropospheric using several methods we're going to discuss. But for the turbulent, it's actually have like from 2 to 5 centimeter delay, and its spatial scale is very small, from 1 to 5 kilometers, and it actually can be mistaken for other deformations. For the atmospheric delay, we discussed that, and it actually have a spatial scale of hundreds of kilometers, so it can be easily removed its effect from other sensors like C-band or X-band if it was existing. So this was like a quick introduction. So in order to find the tropospheric delay correction, we divided into some kind of classes. First, these kind of classes is actually like empirical and additional data, and numerical weather model, hybrid AI, and the time series analysis, which actually the oldest method we have for atmospheric correction. The thing is, there is no single solution is adequate. We have to these classes can complement each other in a real workflow, depending on the process, depending on the phenomenon we are studying and the data available. So for the elevation regression, there is many evidence that the delay of the tropospheric delay is actually depending on the elevation. When we're going up, it is reduced. So it can be modeled like for a linear or a power law. And then, as we can see here, that we can model the atmospheric delay between two interferograms, and this is the left side, and it's actually correlated to the dim elevation from the right figure. This kind of method does not use any external data. It is just based on the data itself or the interferogram itself. It is what we can say, it is like a first start or first step, but it's highly not recommended for many accurate applications. So in order to refine this kind of thing, we have like the GNSS Zenithal total delay interpolation. We have, in order to correct the atmospheric interferometric SAR for the atmospheric delay, we need a dense GBS network. In order to use this kind of the atmospheric delay observed by the GNSS to correct the atmospheric delay in the InSAR. These kind of dense network actually exist in very few places in the world, like in California or in Japan. So these kind of things, the strengths of this method, actually, it is very good. It's very accurate. So it can really capture the stratified and the turbulent effect if it's dense enough. The main problem, it is actually the sparsity of the GNS. If we can see here in California, in the West Coast, we have a very dense GBS observations, but in the middle of the USA, we can find it's becoming very sparse. So the accuracy of this kind of process, of this kind of correction, mainly depend on the sparsity or the density of the available GBS observations. Here in Japan, we can see that it's actually covered with the GeoNet network, the GBS network in Japan called GeoNet. And when we focus on like Chiba region, we can see that using only the atmospheric delay observed by GNSS, we can make a nice correction just by direct interpolation between the GBS observations, just using kriging or inverse distance weight, especially when we have like a flat terrain or not very rough terrain, we can just use kriging for direct interpolation between GNS observations. And we have another process. It's actually iterative tropospheric decomposition model, which actually the baseline of the service called GACOS for correcting the atmospheric delay. The main thing, it uses the GBS stations or the observed delay for the GBS station to fit a model. This model is actually a power model for the stratified delay and just a turbulent model that will be interpolated directly. And we can see here in this image, we have the raw interferograms and the stratified delay correction just by modeling the delay using a power model. We can see here in the second part of the equation. And the final total delay is by interpolating the residual into the size or the pixel size of the interferograms. We can get the total delay correction. These kind of methodology have proven to be very accurate. It can get down the InSAR or can get the atmospheric delay down to a standard deviation of a few millimeters, maybe 4 or 5 millimeters. But mainly, as I said before, it depends on the density of the atmospheric delay of the GBS stations in this kind of in the study region. So if we have GBS station, it would be fine. If we don't, we still have to look for other options. This kind of just a small summary that say that for the elevation regression without any other additional data, it can be moderate for corrections. But if we have a GNSS zenithal total delay, it would be the best to use it for atmospheric correction. Now we have the second class. This kind of class is actually the numerical weather model. These kind of models have like taken the InSAR by storm. It was global, it was accurate, it was easy to understand, although it can be computationally heavy. It requires a very smart programming in order to make this kind of work easily. As we can see here, we have like two main numerical weather model, the global model and the regional or mesoscale model. The thing is, for this kind of numerical weather model, it is actually very good in correcting the stratified delay. It can actually capture the stratified delay or the elevation dependent, but because of the high spatial resolution or very large spatial resolution, the turbulent delay is actually cannot be corrected effectively, and there is many studies for that. So the strength here is actually it can work in all weather conditions. It is available 24/7 for nearly more than 70 years. It started from 1950 until today. So, but actually it have computational cost, and it can be, there's some studies or some cases that can be unreliable. So this is like a list for the global scale models. We can see that one of the most effective or one of the most famous is the ERA 5 model. It is actually an update for the ERA intern. It is temporally updated every hour. So it's very good for the turbulent or the temporal change of the atmosphere, because it have an hourly update. However, for the spatial resolution, it's nearly 31 kilometers. For the HRES, which is the high resolution, it's updated every 6 hours, but the spatial resolution is nearly 14 kilometers. For the HRES, it is actually the model that used for GACOS, and ERA 5 is the model that used for by APS. Actually, this model can use several delay models, but it is the main focus or the main application for these kind of models. We have another regional scale, like the WRF or the MSM in Japan. These kind of models that actually updated very frequently and have a smaller scale. But the problem is it is actually only for the region it was modeled. So for the MSM, it is only effective in Japan. It cannot be used globally. Okay, for the general processing, because this is actually many papers that actually working on this. So when we download this kind of data, the numerical weather model, we have to get some kind of information, which is actually the pressure levels and geopotential level and the water vapor and temperature. From this kind of information, we estimate the pressure, the water vapor, and the temporal delay. Then we estimate the dry and wet delays using this equation. This equation is actually the first part is for the pressure, it's the dry delay, and the second part, the integration along the electromagnetic path, is actually the wet delay. Many processes or many papers is actually discussing how to use this kind of data in order to get atmospheric correction for the InSAR. We can see here that we have like 37 vertical layers from the 0 elevation until 50 kilometer elevation, and the pixel size is nearly 31 kilometer by 31 kilometer for the ERA 5 data. So just combining these and with the DSM. So the thing is, most of the research now is actually working on this modeling and interpretation. There is different schemes and different models that actually uses the same input data for the numerical weather model and just suggest new modeling technique, like using like linear regression or power regression, or recently there is like inverse distance weight interpolation and other kind of interpolation in order to just reduce the pixel size from 31 kilometers into the size of the interferogram pixel size. This kind of this slide shows the main operation of most recent processing for the numerical weather model for correcting the atmospheric delay. So the most used model, as I said, it's actually the ERA 5 and the HRES. It's the spatial resolution in the degrees is nearly 25 degrees, 0.25 degrees for the ERA 5 and 0.1 degree for the HRES. But this kind of model is actually can be downloaded in other formats. The format that we download these kind of models is actually unusable. We cannot use that directly to correct the atmosphere. So the atmospheric delay for the InSAR. So we need to make a process. So this kind of process we have bright researchers have gave us these kind of models like PyAPS and GACOs and ICAMs. These kind of models that can be downloaded or can be processed locally on the PC can use this kind of models like the ERA 5 and HRES and estimate accurate atmospheric delay based on the numerical weather model for the interferometric SAR. So for just a quick view for the PyAPS, we have here the data on the far left side and the estimated delay for the ERA. This is the ERA 1 because this is the paper for Jolivet. It is the main paper for the PyAPS. And he demonstrated that the residuals or the effect after applying this kind of PyAPS correction using the numerical weather model, the fringes have reduced very much drastically in order to make the interferogram more usable and more accurate for estimating this kind of deformation or the deformation we need. So for GACOs, the same thing in GACOs. But GACOs, it started like a model that can be downloaded. Now it's an online service. The main thing in GACOs that is actually dividing that delay not into wet or dry. It's divided into elevation dependent and turbulent, and then it's added together and then apply the correction. The original proposal of GACOs, it was actually using the GPS observation, which was very accurate. And then it was merged with the numerical weather model. But currently, the online service is actually using only the numerical weather model, which can be which have an accuracy far worse than using the GNSS or the GPS. So for the ICAMs, this is actually quite interesting, because this software actually used the 3D model of the atmospheric delay in the latitude, longitude, and elevation, and just use an interpolation to follow or ray trace the InSAR signal in order to get an accurate estimation. As we can see here, it makes this kind of ray tracing and make the 3D interpolation to the size of the pixel size of the atmospheric delay of the InSAR pixels. This kind of method produces a very nice result, compared to PyPS and GACOs. The main issue, it's very heavy and very processing demanding for the interpolation, as we can see from this kind of figure. So for the numerical weather model performance, this kind of analysis, I'm currently doing that with my team. We need to find the performance of these famous models like GACOs and ERA5 for the PyPS. So in order to do that, we didn't use the methodology that is used in other papers. Mainly in many papers, just using the interferogram before and after correction and estimate the standard deviation or the rate of decreasing standard deviation. But here we are just estimated the zenithal tropospheric delay and compare it directly to the observation from GPS data. So we tested the yellow region in California and the yellow region in Japan, and we tested that for nearly 4 years, from 2020 to 2023. We used an observation every 12 days just to mimic the Sentinel-1 observation timeframe or the orbit of the Sentinel-1. So we have here the result for the single path. We have here the result of the single path or of the zenith direction. We can see a very interesting result that the GACOs is actually having a mean absolute error of 6 millimeter and PyPS is actually 14 millimeters. But for the histogram, we can find that the GACOs is actually more centered, which is actually the HRES model. It is actually more centered around the zero, which means that there is no base or main or systematic error in this kind of observation. This is mainly attributed because of the small spatial resolution. The HRES actually uses a 9-kilometer spatial resolution, while the ERA5 is actually 31-kilometer spatial resolution. And when we did this analysis to the Japan, we can find that the effect is different. This is actually quite interesting because the same model performs in Japan differently than in California. We can see that the mean absolute error for GACOs or HRES is nearly 13 millimeter compared to 6 millimeter in California. And we can see that the shift is actually different. For the PyPS, it's actually 20 millimeter compared to 16 millimeters. So it is the same model, or actually two models. We actually tested two models, the PyPS and the ERA5 and HRES. They perform differently from in California compared to Japan. This is mainly because of the different climate regions. So this actually the single path, one direction. But in InSAR, we need two paths. So what we did is actually estimated the differential and multiplied by 2, like we are estimating the differential delay for InSAR. So the result, we can see here that the atmospheric correction for California, the mean absolute error of GACOs become 14 millimeter and PyPS it's 18 millimeter. And it's now centered. It is now centered, which actually understandable because when we are differentiating two sets of data that have the same base, it will be centered around the zero. But for Japan, the errors is actually have increased like 33 millimeter for mean absolute error for GACOs and 33 millimeter as well for PyPS. This result shows that a 33 millimeter or nearly 3 centimeters error for atmospheric correction using numerical weather model is far from acceptable from InSAR. Mainly, if we have like a TerraSAR X, it's actually a wavelength of 3 centimeters. If we have a Sentinel-1, a wavelength of 5 centimeters. So it's almost 2/3 of a fringe in Sentinel-1. So these kind of models that can be used, but not alone. So in order just to get that grasp here, we can see that these kind of errors between Japan and California, it's actually different. So when we read a paper and we do some kind of analysis using numerical weather model, and we have a verification of results from accuracy verification in California, it does not mean that it will perform the same in any other region of the world. It mainly depends on the accuracy or the region. So as we can see, that is actually we need to make or evaluate the performance of each model in each study region. So this is the interferogram or the interferogram for Kumamoto earthquake in Japan 2016. This is the raw line of sight deformation. It have a standard deviation of 3.6 centimeters. So after applying gaps, we can see that the standard deviation have increased. It's 8.6 now. And after applying ISPRS, it's 9.5. So even when applying the numerical weather model, it can improve in some cases, but it can make the interferogram worse in other cases. So it has to be used with care. Each study or each study region need to be carefully evaluated in order to see whether to use this kind of corrections or not. And another case we have here, like this is earthquake in Miyagi, earthquake in Japan 2021. This is the raw line of sight deformation. It's about 1.7 centimeter of standard deviation. After using GACOs, it reduced to 1.4. After using ISPRS, it becomes 1.6. So we can see here that the performance of GACOs is better than ISPRS, but both improve the atmospheric or the corrected part of the atmospheric delay. However, when we just use this kind of results is based on the standard deviation of the whole image. But we can just use a moving window. We use the moving window of 5 kilometer by 5 kilometer in order to calculate the local standard deviation of each part. We can see here, this is the local standard deviation of the line of sight deformation for Miyagi. This is GACOs and this is ISPRS. We can see in this part that the local standard deviation have increased. So although when we're evaluating the whole image, we can see that GACOs actually reduce the atmospheric delay or improve the quality of the InSAR in the image as a whole. But in this highlighted region, it actually becomes worse. So we can see here that the performance of the numerical weather model can actually vary within the single map. So this is actually another problem that we need to carefully study in our work. So going through quickly for the artificial neural network, this is the third class. Actually, the AI have gained attraction for many applications in many fields, especially in remote sensing. The main issue in our study that it requires a lot of data for training, and it requires and there is different model like dense model or 2D or 3D convolution neural network or ResNet or transformers. In order to build this kind of data, of this kind of model, we need to train these models. We can use GNSS observation, we can use numerical weather model, we can use simulated data. Each one of these have its strengths and its downsides. For the GNSS, it is not available in many regions in the world. And the problem is this kind of models is actually performed locally. So it can be performed well in the training region, but in other regions cannot perform the same way. So here is a model, we processed that with my team. This is a 2-head dense model. This is just working on the single pixel. So it just uses the elevation and the estimated delay from the error 5 using this kind of 2-head dense ANN model to get the refined total delay. So in this kind of data, we use the GNSS or GDS observations in Japan in order to train this kind of model. And we can see here that before training, we have like mean absolute error of 15 millimeter and root mean square error of 20 millimeter. After correction, it reduced to 12 and 16. So we can get some kind of improvement using this kind of models. This model is actually performing pixel by pixel. It's not like convolution. However, it is only used for the local region that was trained on, and if it was transferred to other region or applied to other region, the result is not predictable. And this is other paper was published. It was very exciting. This kind of model, they used the 3D autoencoder to correct the atmospheric delay using a very small time series, nearly 9 interferograms. But they use nearly 25 million series in order to train this kind of model. This model is actually used to estimate the deformation in the fault and local depression. The thing is about this kind of model that it was trained using 25 million series to distinguish between atmospheric delay and just 2 deformation signature, the depression and the fault. Just these 2 deformation signature using this massive training data set. This model actually trained using synthetic data set, not actual. And this is other model that use 3D convolution neural network to correct this kind of atmospheric delay. So the thing is, why it is not very accurate, or why we can use this with the utmost care. The thing is, this kind of model does not understand the atmospheric delay. It is just try to isolate or remove any signal that you can see spatially correlated and temporally uncorrelated. That's it. They don't understand the physics of this kind of model. It's just like a high end or a high level filter, just filtering this kind of signature. So for the last category is actually the oldest category we have is the time series analysis that actually uses the atmospheric delay signature for it is being spatially correlated and temporally uncorrelated. And this kind of method assumes a linear model or other model for the temporal deformation, fitting that model in order to correct the atmospheric delay. This is the Alexandria city, and this is the deformation in one of the pixels that have, as we can see, this analysis spanned nearly 10 years from 2014 until 2025. And this kind of deformation we can observe in one of the pixels. We can see that the linear line or linear fit is actually the deformation direction, and all these cutters point is actually the range of the residual error that mainly due to atmospheric delay. So this kind of images, this is a list of interferograms in Marsa Matruh city, north coast in Egypt. The problem, as we can see, that now we in the age of big data, we have large data set, and as we can see that these kind of fringes are all interferometric delay or atmospheric delay. It can be changing in the pattern, in the direction, in the amount, depending on the location and the time. So we need an accurate method in order to correct for these. So one of the things that was proposed before is using the ARC solution, which actually using the differential observation between 2 pixels, and the space between the 2 pixels nearly less than 1 kilometer. This observation, we would assume that it is free from atmospheric delay, and then use this kind of solution to estimate the deformation and baseline error, and then we estimate the residual, which would be the atmospheric delay, and then we correct the whole images and then do the reprocess. So for this kind of time series analysis, we have many strengths. For instance, we do not need an external data. It is effectively reducing tropospheric noise, and it is scene specific, so it can be used for a simple scene. For one scene, it is compatible for standard technology, and the ARC-based model is actually enhancing it. One of the many limitations we have that it requires a large data requirement. In order to filter out the atmospheric delay that's temporally uncorrelated, we need a lot of images. It is not suitable to single interferogram, and it's limited. The performance is actually limited in vast varying atmospheric delay. It is computationally intensive, and it mainly depends on temporal stability of the target. If the pixel have a low coherence, it will not perform as well. So the main question, what method should we use? Well, the simple answer, it depends. There is no correct answer for everything. It depends on the additional data availability. Do we have GNSS or GPS observation or not? The topography and the climate of the study region, what kind of region we are studying, the availability of SAR image. Do we have a large InSAR stack or small large stack? The required accuracy and available funds. It depends on the project. When we have a project, we have some kind of fund. It depends on how we are able to facilitate the correction in this large data set. So this kind of graph can help in order to select the best method. So first thing we have to ask ourselves, do we have GPS? Well, if we have, that's great. We have the GPS. Is it dense? If it's dense, and then we can ask ourselves, what about the terrain? If it's flat, we can just make a direct interpolation using kriging or something. If it's not flat, it's rugged or rough, we can use the iterative tropospheric decomposition that actually isolates the troposphere into two components. If we have a sparse or GPS observation, we want to use them. It will be a very helpful asset. So we need to combine them with numerical weather model and give the advantage or give a higher weight to the GNSS observation. Well, as most of the regions or most of our study region, we do not have, if we don't have a GPS observation. When we look at the data set, if we have a large data set, we can ask ourselves, is the tropospheric delay low or high? If it's low, we can use time series analysis like it was proposed before in many, like in INSAR or ISPRS. If it's a high atmospheric delay, we need to incorporate the numerical weather model with our process. If we have a small data set, then we can use the neural network. If we have a high tropospheric effect, we can use the numerical weather model with the neural network. If we do not have a high atmospheric delay, we can use the neural network only. So this is like a quick graph, just a small guide to see how to use this kind of atmospheric delay. So the main thing is actually the ground truth data is the best thing to use, then the data specific analysis, and then actually the neural network shows promise, but we need to use it with care. So this is like an example for the north coast of Egypt. This is a study we conducted in order to correct. In this region, we do not have any GPS station. So at first, we used GACO's atmospheric delay. After applying this atmospheric delay, the thing is we reduced the effect of atmospheric delay significantly in the images. Then we use this arc solution method in order to find the residual. And by combining the residual and the atmospheric delay from GACOS, we can get the final atmospheric delay for the image and then complete our analysis. So for the challenges we have, we are just summing up the presentation for the challenges for the empirical, for the elevation dependent model. It's highly unreliable. For the GPS station, it is limited and sparse. If we have the GPS station, it would be the best options. For the numerical weather model, it's actually spatial and temporal resolution mismatch. It has a very large spatial resolution and temporal resolution, and we need to do a lot of processing in order to downsample this kind of scale into the INSAR images. It actually, the turbulence effect is undersampling, and they have data latency and processing costs. For the hybrid and AI, it actually can be used for scales less than 1 kilometer, but the main thing, it is the generalization have some kind of issue. For the interferometric, for time series, the data and the processing is extensive. This is like the thing is. For the future direction, for the now we have a rapid climate change. So this is actually altered the humidity pattern. And we have extreme weather events now becomes very frequent, like the typhoons and cyclones. For the atmospheric delay correction, we need a research to support the new mission like NISAR or ELOS-PULSAR. For the AI approaches, I believe that in the future direction we are using now, the direction is going to the physics-informed neural network. So it is not just filtering the noise. The model understands, or should understand, the effect or the physics of the atmospheric delay itself and correct it accordingly, not just working as a high-end filter. Now for the age of big data, we need an accurate automated correction method or approach. a method that can fit all. Currently, we don't have a method that can fit all. But for the future direction, we believe that we should, or we need one thing fits all. For the possible direction, or the things that personally I hope that it will exist. For the Google Earth Engine, it currently offers a corrected Sentinel-1 SAR GRD ground range distributor. So is it possible in the future to provide a Sentinel-1 SAR phase corrected for atmospheric delay? Well, actually, we are not sure about that, but if it's happening, it will be a very nice thing. So thank you so much for your attention.
Thank you very much for this impressive talk and overview about all the different atmospheric correction possibilities. Now, as always, the floor is open for questions, and we will receive them both in the webinar chat as well as in the question and answers panel. And I see that in the question and answer panel, we already have received a number of questions, and I will start reading them to you. So the first question I read is, based on your experience, which platform does atmospheric correction in a better way for a long-term analysis? And with platform, I believe algorithm or framework is meant. The person asking the question refers to GMT-SAR, ISPRS, MinPy, and so on as examples. So what of those frameworks, APIs, in your experience is best?
Yes, I think he believes in, he means the coding or the packages in the coding. Like the Python, he believe he asked about the package that we use in programming. Mainly, I use the Python for programming. But for actually, I found that when we are using a model, like numerical weather model, after we download the data, it is just becomes like a CSV file. So it's for me personally, I do the program because the code is not very difficult. It just needs some kind of just coding in order to be light on the processing, just using like multi-processing or something. But for the processing itself, it is I believe it's quite simple to code. But if you don't want to code, I believe PyAPS is actually a very nice, a very simple to use alternative. PyAPS, after installing, it's very easy to install. It will automatically download the Aero5 data, process it, and then give you the atmospheric correction for a single date or for the InSAR, for the interferogram. So it can be used to estimate the master and slave, and then estimate the correction between both of them. So for my answer is PyAPS would be much better, yes.
Okay. Then another, let's say, related question is, do you know which corrections are applied in the standard interferogram processing software such as Gamma or ISCE? So do you have any information on that?
No, I know that it has some kind of filtering, but it is not. In order to apply atmospheric delay, you have to set the atmospheric delay correction itself. Like in MintPy, for MintPy, when you're using MintPy, you can select what kind of atmospheric delay to use. You can select the PyAPS or GACOS or even elevation dependent, which is the first one we examined here, or even do not. You can select that you will not. You can select not to apply any atmospheric correction. So I believe it depends on the software itself. So every software, it has the option to apply or not to apply the atmospheric correction.
But you don't know which algorithms are implemented in those software packages.
I didn't. I study MintPy, but I didn't do an extensive processing on ICE. So in ICE, I used ICE before, but I actually found MintPy is actually more suitable for me. So.
Okay. And then you just mentioned an elevation dependence, and we also have a question on that. Another person asks, in most packages, a digital terrain model is used for tropospheric correction and not a digital surface model as mentioned in your slides. Do you believe that this provides a negative effect on the results?
Yes, actually, using just an elevation dependent model is actually not very effective in correcting the atmospheric delay. We just use it if we don't have any other options. That's it.
Okay.
Mm-hmm.
Then another question is, can you integrate GNSS, weather models, and AI together to get better results in the atmospheric correction pipeline? So what is your impression here, your opinion here? Do you believe one can create a new model?
Well, yes, of course. We can implement all of them. Actually, and for the Gakos paper, the paper actually implemented the numerical weather model HRES and GNSS delay in mathematical model, not even a neural network, and get a very good results. So it can be quite straightforward if we just got the Gakos result and filter it using or improved it using AI, like the model, that two-head model I just presented, or we can just add all of these data into a single model and then training. It would be quite challenging in the programming because we will enter the numerical weather model as an image to the image. We're gonna enter the GPS pixel as points. So we need to just fit these with those. And I think the current model that uses this kind of data is actually the transformer. And as we all know, that transformer is very extensive in processing. It requires a lot of nodes in order to make the encoding and this kind of process. So I think it can be done, but it depends on the model you are trying to build.
Okay. And then we have a closely related question. So another person asks, since there are no ground truth values of atmospheric delays, how can artificial neural networks be trained in the first place? So do you always have to rely on simulated data? And how does this then work on actual real world data?
Mm-hmm. Well, this is actually a very good question. The thing is, the only observation, or for us and in the remote sensing, we have a ground truth data, but this is actually the observation of GNSS. For the GPS observation, we can get an atmospheric delay estimate for nearly 5 minutes interval for like 20 or 30 years now. In GeoNet Japan, we have like a continuous data for more than 30 years now. And it contains the atmospheric delay or tropospheric delay. This we consider as a ground truth data. But for other regions, we actually don't have any choice. We can use the numerical weather model for training. But as I mentioned before, that the current presented new AI models is actually based, or they used synthetic data, mainly because they require a lot of data, nearly 25 million time series. So we do not have an actual observation for this kind of data.
Okay. And then let's come to the last questions because time is running out. So we have a question on, is there a way to tell apart strong or high and small or weak atmospheric effects in the data?
It is, yes, it's very nice question. The thing is, we can determine visually or by using standard deviation. So if the standard deviation is very high, we can determine that it has a very large atmospheric delay. Other thing, we can estimate the correlation between the delay and the elevation for the rugged terrain. If they have a strong correlation, now it is actually based on the atmospheric delay, not a deformation.
And is there a way to understand whether any corrections were applied correctly, like some sort of proof?
Actually, this is something we are working on it right now. I presented part of our work that here. This is the local standard deviation. We can see that this is the local standard deviation for the pixels. Yes, we have the Gakos actually performed quite nicely. It reduces the standard deviation from 17 millimeter to 14 millimeter. However, when we are using this kind of local standard deviation, we can see that in part of the image, the standard deviation have increased. This means that the phase become unreliable in these parts. So I believe this is part of ongoing research now in order to filter which atmospheric correction can be used. And if we applied atmospheric correction and it performed well, should we use it in the whole image or just part of the image?
Okay. And now, last question, which also has a nice, let's say, outlook twist. Do you believe that advancements in atmospheric corrections influence or improve our understanding of long-term environmental processes? So do you believe that this makes an impact also on studies regarding important topics such as land subsidence or climate change?
Yes, I believe so. It is very important. The thing is, when we are studying InSAR, we are studying a small region, not a very large. But the climate change is actually a global phenomenon. So as I can see, that when we have a change in the climate, this is the global phenomenon can affect our small region of study, that the InSAR. So we can see some kind of relation, but I don't believe that is studying a time series of a small region of InSAR can actually affect or improve our understanding for the global phenomena of atmospheric delay, of climate change, or what I mean. I think this is like apart from the whole. So we still need to study the whole in order to get to the part.
Okay, I think these are very nice last words. We are a little over time, or actually still quite good in time. It's more or less 3 p.m. straight. Thanks again for the presentation. Thanks also to all the people who asked questions and gave us a nice and vivid discussion. I believe there will be an upload of today's talk on the ISPRS webpage, so that all the people who asked for recordings or for slides can have a peek into that as well and can rewatch to get their questions answered. Thanks again to everybody. And with this, I conclude today's ISPRS webinar.